is Ralph Dornsife. He's a licensed civil and structural engineer with Washington State Department of Transportation.
Thank you very much for the introduction, Rich. I think everybody here in the room can probably agree that an inordinate percentage of all bridge preservation maintenance issues are somehow related to expansion joints and bearings. If we could somehow wave a wand and wish away half of those problems, it would make all of our lives a lot easier. There are many good and a few bad expansion joint and bearing systems out there. We try to phase out and replace the bad ones. We try to improve upon the mediocre ones and expand the usage of the most dependable ones. So with regard to the performance of even some of the most dependable systems, I've found a very wide range of varying perceptions, both within our department and then when I talk to other states. Well, for instance, modular expansion joints. We've had very good success with them since we adopted fatigue resistant design specification back in the 1990s. I know other states absolutely abhor them. As Tripp just mentioned in his presentation, if you talk around the nation, armored strip seals are probably one of the most robust systems preferred. But even within my department, I have one district which absolutely despises them. So serving as the expansion joint and bearing specialist for Washington State DOT, it's really provided me a lot of opportunities to talk with maintenance staff as well as with bridge designers who are involved in repairing and replacing systems. It's also given me the opportunity to isolate and examine some of the problems that we've experienced in our different systems. So what I've really found from all of this over the years is that proper handling and installation supported by knowledgeable inspection plays just a huge role in how these systems perform as well as their long-term durability. So I've also come to the conclusion that if we spent a little bit more time up front addressing some of these factors, we really could significantly reduce the incidence of expansion joint and bearing problems. So in the next few minutes, what I'm going to be doing is stepping through a series of case studies, pointing out some common handling and installation issues. I will discuss the methodology we use to diagnose the cause of some of these problems, which I think will be helpful for maintenance people. And then I will follow that up with a discussion of some collaborative methods that I believe can be used to enhance installation quality and to mitigate or prevent the kinds of problems you're going to be seeing on some of these slides. So we're going to be taking a look at 7 different bridges, 5 expansion joint. 5 bridges with expansion joint issues and 2 with bearing issues. And we're going to start right off with the I-5 southbound Blakeslee Junction Bridge. So this bridge is located near Centralia, Washington. It was constructed a few years ago as part of a capacity enhancement project. As such, the work on it was staged and it wasn't open to traffic until about 8 months after it was completed. Soon after the bridge was open, the concrete was observed to have spalled out adjacent to the armored strip seal joint edge rail, as you can see in the photograph right here. So in an attempt to determine the cause of this failure, we pulled our inspector daily reports as well as photographs from when the expansion joint was originally installed. So as a prelude to telling you what we found, I've shown here a rendering that I excerpted from the manufacturer's approved shop drawings. It shows how an armored strip seal system is supposed to be installed. So the assembly is suspended using a pair of erection angles from the bridge deck over the blackouts. And then you can see the threaded studs which are welded to the tops of the edge rails. You have a pair of double nuts which engage a slotted hole in the erection angles right there. And what the system allows you to do is allows a contractor to set the rails to the profile of the bridge deck. It also allows the contractor to set the gap opening to correspond to what that gap opening should be when the bridge deck is at the temperature at which the concrete is poured into the blockouts. So it's a very simple yet elegant way of installing these. The double nutting system also allows the contractor to loosen the upper nut immediately after the concrete sets, after it's poured into the blockout. And so that allows the joint to open and close as the bridge expands and contracts after the concrete placement. So we went back and we looked at some of the original construction photos, and you look at this picture and from a distance, nothing really looks too amiss. If you take a little closer look, you can see short sections of steel reinforcement bar that have been welded to the tops of the steel frame rails. The date stamps on these photos indicated that these bars had been welded at least 5 days before concrete placement. So clearly in non-conformance with the contract drawings as well as the approved shop drawings. So the inspector daily reports provided us no information as to when these bars might have been removed following concrete placement. So we took a look at official temperature records for Centralia, Washington, and those showed that the ambient air temperature had fluctuated as much as 30 degrees in the 24 hours immediately after pour. So even recognizing the lag in the structure temperature relative to the air, we calculated that the unimpeded motion range of the joint was probably as much as 3/8 of an inch during the 24-hour period immediately following the concrete placement. So I returned back to the original photo, and you can pretty clearly see a plane of delamination that is collinear with the horizontal studs embedded in the concrete, and this suggests really that the immature concrete had experienced distress as a consequence of being unduly restrained. So our investigation on this one concluded that the contractor's failure to remove the welded steel reinforcement bars immediately following concrete placement was the most likely cause of the failure here. The restraint imposed by the bars prevented the joint from opening and closing with temperature changes, and this resulted in a cracked plane of weakness in the concrete, which eventually spalled out under traffic. So had the contractor followed the installation procedures delineated in the approved shop drawings, this obviously would not have happened. So we move on to another armored strip seal expansion joint, the I-5 Dike Road Overcrossing Bridge. This was installed in 2012. The original joint that was here before this one was a spring-loaded steel sliding plate system that we used extensively back in the late 60s and early 70s. Those were extremely maintenance-prone systems. We were fortunate to have gotten 40 years of design life out of it. So after we installed the armored strip seal, several months after installation, the new frame rails began failing over the abutments. So within about 2 years, the frame rails in the heavily traveled rightmost lanes had become so loose that we had to remove them. So we commenced an investigation in 2015 to determine the cause. So we first did an on-site inspection. We saw that the remaining frame rails over the abutments were displacing under wheel loads, and this indicated that the welded connections had failed or the rebar loops were moving within the concrete. So also, we found that there were elastomeric seals at both abutments that had fallen out and were drooping underneath the joint. So as you can see here from the picture, the temporary support system shown here largely conform with the approved shop drawings. However, note the position of the threaded studs in the slotted holes. So even if the upper nut were loosened immediately after concrete placement, the joint could still not close. And you can also see the blocks in there which would have impeded the joint from closing further. So this was probably the most likely cause of the failure. So this is a photograph of the detached elastomeric seal, and you can see the lobes had been lane striped upon completion of the work, and this indicates that the seals had never been fully installed in the first place. So Qualified installation technician or a well-trained inspector should have been able to identify both of these deficiencies. So we move on to a project in the Olympia area, Interstate 5. This is a photograph of one of several 30-year-old armored strip seal expansion joints that just got tired after 3 decades of service and finally wore out. So we decided to replace these with unarmored preformed silicone seal system. So replacement of the original joint entailed the removal of the concrete on both sides as well as the anchorage, a replacement of the blackouts with the new cementitious concrete headers, and installation of continuous preformed seal elements. So this is a photograph of the preformed silicone strip seal system taken several days after it was installed back in 2014. And you can see that the new silicone seals have already debonded from the concrete. So we talked to the manufacturer. They were concerned that there had been a rain event and perhaps the concrete was wet at the time it was installed. So the contractor reinstalled, and we had another failure in a couple days. So we went back again to the supplier, and they came back and stated that a concrete admixture that had been used to accelerate strength gain had apparently caused a chemical reaction involving magnesium and caused outgassing through the concrete, inhibiting the seal and causing the preformed seal to debond. So this kind of really points out the importance of making sure when you're using new components, in this case a different admixture and a different expansion joint system, to make sure that they're compatible with each other. This is a photograph of another of the completed joints from this project, and you'll note the waviness of the seal. The photograph on the right shows the placement of the cementitious concrete headers. So the material that was used to form the joint gap was obviously very flexible and bent over under the lateral weight of the new concrete. Had the formwork been stiffer, or if care had been taken to incrementally place the concrete on lifts on both sides, it probably wouldn't have happened. So obviously not a particularly well thought out process. We move on to a modular expansion joint project. This was a ramp bridge connecting State Route 18 to I-5 southbound near Federal Way. The bridge was built with 9-inch motion range modular expansion joints at each end to accommodate service movements. And shortly after we opened this bridge up, we observed surface cracks adjacent to the edge rails. Also, we had reports of very loud pounding noises. So in one instance, a chunk of concrete adjacent to one of the edge rails actually popped out. So in response to these complaints, we reviewed the construction records and determined that consequent to a misunderstanding regarding clear cover over deck bars, the contractor had not installed transverse reinforcement bars over the tops of the modular joint support boxes. The concrete in that area serves as a deep beam over the primary girder webs, so the absence of the transverse reinforcement bars explained the cracking, but really did not explain the loud noises that were being reported. So we went out and did a site visit. During the site visit, I did a tactile inspection of the top of the edge beam adjacent to the concrete and detected a vibration under heavy truck loading. So our inspection team then walked inside of the steel boxes to inspect the support boxes, and what we observed was that several of the support boxes were moving vertically relative to the concrete they were cast in. So these and several of the other support boxes also manifested water that was seeping through the concrete adjacent to them. So these observations overall confirmed that inadequate consolidation had been achieved underneath the support boxes. So on the right side, I show a photo of what a modular joint looks like from underneath. The load path goes from the wheels above to the center beams, through the welded connection into the support bar, back through the bearings and stainless steel sliding surface in there, into the bottom of the support box, and then you would have concrete underneath here. So if you don't get good concrete consolidation, you lose your load path. Very critical. So our special provision requires a qualified technician employed by the joint manufacturer to be present during the installation of modular joints. In this particular case, the concrete placements had been delayed a day and the contractor sent the technician home a day early. So although the technician had provided written instructions emphasize the importance of achieving adequate consolidation underneath the support boxes, those instructions were either not conveyed nor heeded. So this is a photograph of the construction crew removing concrete from atop all the support boxes and also underneath those support boxes where consolidation had not been achieved. Show this picture to kind of emphasize that everyone is adversely impacted when things aren't done right the first time. So it's not just the agency, it's not just the manufacturer, it's not just the contractor. We all lose, so that includes the motoring public. I'm going to move on to another project involving modular expansion joints. The I-90 East Channel bridges connect Mercer Island to Bellevue, Washington. And this is a photograph on the right of a failed modular expansion joint center beam field splices in the westbound bridge. So this joint was manufactured and installed back in 1981, prior to the advent of fatigue-resistant design specifications. So we're really lucky to have gotten 30 years of service out of this. And after making some emergency repairs, we began planning for its replacement. We prefer to avoid modular expansion joint field splices wherever possible. In some instances, however, the work must be staged, and so you have to make the field splices. And in that regard, we allow either bolted or welded field splices. For the replacement project, the contractor and the modular expansion joint manufacturer opted for welded center beam field splices. Because of the spatial constraints and the field conditions, these are often very difficult welds to make, and so our agency required that the welded field splices be ultrasonically inspected. And this is a photograph of one end of the modular expansion joint segments. You can see how the ends of the center beams are beveled at the field splice location. The center beams, as well as the rest of the modular joint, are typically galvanized prior to final assembly. The galvanization needs to be removed at the splice location to facilitate welding. Generally, this is done by the contractor using hand grinding. So in this particular case, for whatever reason, the contractor sandblasted the ends of the center beams, and he did that without masking the stainless steel sliding surfaces in the support boxes, which had been polished to a number 8 mirror finish to achieve low friction. And there you can see that's what was formerly a number 8 mirror finish polish, and it's been totally eroded by sandblasting. So we were informed of this situation 6 hours before the first lane closures were scheduled to begin, and really put us in quite a difficult position. So we immediately contacted the manufacturer to evaluate the feasibility of either replacing the stainless steel or somehow repairing it. The manufacturer advised us that it would be impossible to replace the stainless steel without totally disassembling the support boxes, which was not something we were going to be able to do on site. They did feel that it would be feasible to polish in the field using power hand equipment the stainless to achieve a number 2B finish. So recognizing some work that had been done at the University of Washington for the Wisconsin DOT, which dealt with alternative surfaces for steel sliding plate joints, we opted to allow the contractor to buff these out with a Scotch-Brite pad to a number 2B finish. So we accepted the field polished surfaces and the associated trade-off so that the project could then proceed. We'll move on to a couple cases involving bridge bearings. This is the Nalley Valley Southwest Line Bridge. It's a connection between State Route 18 and I-5 near Tacoma, Washington. It's a 4-span pre-stress concrete box girder structure. and each end of the bridge is supported on a pair of sliding disc bearings. So this is a close-up of one of the bearings that was installed correctly at the abutment. So the movement direction on this is left to right, and you'll note the shipping strap that was installed by the manufacturer for the purpose of assuring that the sole plate was not separated or rotated during handling. You also see the 4 pintles that extend up into recesses formed in the soffit. So once the end segment of the bridge was post-tensioned into place, the bridge was jacked up to a specified dead load, and then this whole area in here was grouted. So at the other end of the bridge, after the masonry plate had been bolted down, it was determined that it was in the wrong location. So we had to pull the bearing assembly out, drill some new holes, install some new anchor bolts, and move the bearings to their correct locations. So somehow in the process of moving the disc bearings, the shipping straps got removed, and you can probably guess what happened. Somehow the sole plate got rotated 90 degrees relative to the masonry plate. So the consequence of this was that the movement direction was perpendicular to what was required. So in lieu of now having to lift this bridge up 5 or 6 inches in order to rotate the sole plate back into position, the contractor coordinated with the manufacturer in proposing a procedure in which the 4 pintles were cut, the sole plate was rotated into its correct position, and the pintles re-welded. So we used thermal crayons to assure that neither the Teflon nor the polyether urethane disc were damaged by excessive heat. And the last project here involves mishandled elastomeric bearings. The photograph on the left shows an elevated roadway deck of the recently opened SR 520 replacement floating bridge. The precast concrete deck elements were set on false work, as you can see on the right photograph. Once they completed closure pours and post-tensioning bidirectionally, the false work in there was eliminated so that the bridge deck then sat on bearings. The bearings are located where the yellow arrow is shown on here. So this is a photograph of one of the steel reinforced elastomeric bearings. You can see that it wasn't detailed well, inadequate space available to tighten the bolts, and so the contractor apparently chiseled out a chunk of the elastomer as needed so the bolts and wrenches would fit. So not a very good solution. You can see here that one of the steel reinforced elastomeric bearings, you can see the shims, the exposed steel shims there. It's probably one of the worst areas to damage these bearings because that's where, at the edge of the bearing is where the shear stress is between the elastomer and the steel shims are greatest. So I'd like to shift gears just a little bit and briefly touch upon and discuss upon some ideas and concepts to help avoid or mitigate some of the problems that I've shown here. Our special provisions require that a qualified installation technician be present during installation of more complex systems. In order for this to really work well, there needs to be both an acknowledgement and an appreciation for the role and the value added by the installation technician. To add value to the project, it's very important that the installation technician be qualified, both in regard to experience and to his conceptual understanding of how the system operates. And it's extremely important that the installation technician be present at critical times. So in the case of the Triangle project, it really made little sense in retrospect to send the technician home a day early before concrete placement. In the case of the East Channel Bridge, had the technician been present, I'm sure he would not have assented to the contractor sandblasting the polished stainless steel surfaces. I really can't overemphasize the importance of the owner agency's inspection staff in ensuring that systems are handled and installed in the correct manner. And this is especially important when the qualified installation technician is not present during the installation. Experience and knowledge, especially as it's specific to expansion joint and bearing systems, is very critical and important. Expansion joints and bearings often receive less attention than other systems because they're usually handled last and considered to be ancillary components. So what we found in our department is specialized just-in-time training for inspectors has been very helpful. So a few years ago, we had replaced a number of modular joints on some of our Columbia River Bridge crossings, and we did just-in-time training, and it worked really good. It gave us a chance to familiarize inspectors with the operational characteristics of modular expansion joints, and also really gives them an idea of the key things to look for during inspection, and also develop some working relations with our staff in the office. Staff retention these days has been challenging, and that really needs to be taken into consideration in the planning and frequency of training. There's a lot of different skills and talents required to produce a durable, optimal performing expansion joint or bearing system. And you can recognize the importance of all of these roles. We need to appreciate that everyone in the supply chain comes from a different background. The only way we're really going to meet the challenges associated with the diversity of backgrounds is through effective communication. So a good example of this is getting effective concrete consolidation underneath modular expansion joint support boxes. So obviously the bridge engineer and the modular expansion joint designer understand that. The qualified installation technician likely understands that as well. The construction workers that are pouring the concrete probably do not. And a simple 5-minute pre-pour conference may make all the difference in the world as to whether the installation goes well and is durable and performs as it was intended. Project specs typically require shop drawings and calcs from the expansion joint and bearing suppliers. Additionally, project specs often require contractors to submit written procedures in advance, and this is particularly important when installation procedures are not explicitly shown on the shop drawings. So the review and approval of these drawings and procedures assures that the means and methods are carefully thought out and vetted beforehand, not while the work is being done or after mistakes have been made in field. So this is a case in which we replaced some steel finger joints with a modular steel finger joint system. We replaced it. In the process of going through this, the manufacturer did not supply us with an installation procedure, and so we worked with the contractor to develop a procedure. And the procedure was based upon using the temperature at sunrise, the air temperature at sunrise as a proxy for the superstructure temperature at that time, marking reference lines on the bridge deck. And then that would allow the contractor to install the panels as the temperature changed during the day. And that's the finally installed system. And if you want some more information on that particular project, you can go online. The International Joints and Bearings Research Council has a paper that I wrote for the 2016 Congress, which discussed that as well as some other issues, and they'll tell you a little more detail on that. That's available online. Lastly, I'm going to say that consideration should be given during design also to install systems and their connections to minimize the potential for improper installation. As an example, I showed you a few slides ago where the pintles were installed in a rectangular arrangement, recesses in the bottom of the soffit, and had those pintles been arranged in a rectangular pattern instead of a square pattern, it would have been a way that the contractor would identify the issue before the last segment was post-tension to the bridge. So it's all kind of common sense and design aspects to take into consideration that these things have to be installed, and you try to make the installation process as foolproof as possible.
What's the expected life that you get out of a modular joint?
You know, in past years, 30 years has been about what our life is. I really think that with the modular joints that we're putting out there now, since we implemented the fatigue-resistant design spec, that I think they're lifetime. I think we can get 75 years out of them. That said, there's going to be times where there will be bearing elements that will need to be replaced and equidistant devices. So they're going to, you know, there will be maintenance needs to be done from time to time, as well as seal replacements, of course.
As a follow-up, do you require parts then to be provided, spare parts to be provided as part of the contract, assuming that 75 years from now you won't be able to buy those parts? Or 50 years from now, or whatever?
What we do require is that, as part of the shop drawing process, the manufacturer has to provide a parts list and replacement procedures for replacing those elements. So, yeah. So I think our first modular joint using our own fatigue resistant specification was the I-90 Lacey V. Merle floating bridge. We put those in on 1993, so we've got 25 years on those, and we are not seeing any symptoms of wear at all. So they're holding up extremely well. So that's why I really feel that what we're putting out there now, we should be able to achieve the same life as the bridge.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.